Strip away the plasma physics for a moment, and both of our machines come down to one thing: the field. A stronger magnetic field means a smaller, hotter, more capable machine. The magnets are the machine. The reason we can reach for extreme fields now, and earlier programs couldn't, is a material. It's a high-temperature superconductor, a rare earth barium copper oxide, REBCO for short. It carries current with zero resistance at temperatures and fields that older superconductors simply couldn't survive. Superconductivity isn't a single switch, though. It's a surface in 3 dimensions, the critical surface. A REBCO tape stays superconducting only inside a boundary set by temperature, magnetic field, and even the angle between the field and the tape. Push past any edge and it goes normal. What makes REBCO special is where that boundary sits at high field. Deep inside the material, tiny defects pin the magnetic flux lines in place instead of letting them move and dissipate energy. That flux pinning is why REBCO keeps carrying enormous current in fields that would kill an ordinary superconductor. The field a magnet produces on its axis comes straight from geometry. How many turns of conductor, how much current in each, how they're arranged. More ampere turns, more field. Simple to write down, brutally hard to build. Because the conductor is a tape, thin, flat, ribbon-like. REBCO is grown as a coating just microns thick on a metal backing, kilometers of it, every meter of which has to be nearly perfect. The performance of a whole magnet is set by the weakest stretch of tape in it. You build a magnet by winding that tape. Hundreds, thousands of turns, laid down with tension held to a fraction of a percent, insulated and supported layer on layer. In the burner's plug, this winding is what produces 26.49 Tesla. And now, the material fights back. A current-carrying conductor sitting in a strong field feels a force, the Lorentz force, pushing outward on every turn. In a coil, that force becomes hoop stress, the same stress that bursts an overpressured pipe. It scales with the field squared. At the fields we run, that stress approaches the mechanical limits of the strongest structural materials we have. The magnet isn't held together by its superconductor. It's held together by the steel and the structure wrapped around it. Engineering the field means engineering the forces the field creates. There's energy locked in that field too, a lot of it. A big high-field magnet stores energy that grows with the square of its current, and all of it wants to come out the instant anything goes wrong. Anything going wrong has a name: a quench. If one tiny spot of the tape warms past its current sharing temperature and turns normal, it develops resistance, heats, and the normal zone can spread. Left alone, the magnet dumps its entire stored energy into that spot. So quench protection isn't optional. It's a whole discipline. You detect the quench in milliseconds, then deliberately spread it or extract the energy so it's dissipated safely across the coil instead of destroying it. A high-field magnet program lives or dies on how well it handles a quench. Put the number in context, because context is the honest part. The 26.49 Tesla in the plug is 0.82 times a demonstrated superconducting record. We are asking the magnet to operate inside capability that has already been shown in a laboratory, not to invent a new physics record on the critical path. That's the discipline behind the headline. Not, we need an impossible magnet, but we need a very hard magnet built from a proven material, engineered against known forces, protected against a known failure. This is a conceptual design, validated in open simulation, not yet an operating machine. But of everything we have to prove, the magnets are the piece that rests most firmly on what the world has already built.